Let's talk next here, start anyway, talking about, a few minutes on, line integrals. Line integrals. Now, the difference between what we've been doing, talking about integrals, single integrals, is we are kind of going back to start with anyway. A single integral. However, a line integral is going to be an integral that's integrated with respect to or over a curve instead of an interval a to b. Right? Because that was the way we started integrating, was integrate over a to b, right? Not yet. We haven't done this quite yet. Because here's what we're talking about. So we've got this curve. And this is the notation. Well, kind of hit the notation here, but so we're integrating. We're kind of used to this. We're integrating single integration though over a curve C. So we've got some curve C. That we're integrating over with respect to. So we're going to integrate over that thing, this function. So this function is different usually than the curve C. Okay? Now, the reason ds, if you recall, s was kind of what we used for arc length. And so that's how we're going to handle this. Because as we go from here, this point to this point, what we're not taking increments with respect to the x-axis now. We're taking increments with respect to this curve here. So hence, arc length is going to play a major role in doing this. So we're going to go incrementally along the arc length, and so each one of these little pieces is basically delta s, and so hence we wind up with a ds instead of a dx or d something else. Okay. All right. So let's recall, because we'll definitely see it here. If we had, and we're going to go with respect to a parameter t, because to describe these things, it's best to do it in terms of a parameter t. And so we're going to define our curve in terms of parameter t. So x equals some function of t, and then g, y is some function of t as well. We're going to use that to describe our curve, and hence we'll also have to describe our function in terms of those parameters also. But as you recall, arc length equals, or what it equals in terms of this parameter? Well, it turned out it was t equals a to b, the square root of derivatives, right? dx dt squared plus dy dt squared dt. That gave us our arc length. Well, turns out then here's the way it goes. So you can kind of see. Let me just show you what the definition of this is. Move this over a little bit. All right. So the line integral over curve C, f of x y ds equals the integral from a to b. Rewrite f of x y in terms of the parameter t. We have to figure out what those are. But so we rewrite f in terms of x of t, comma y of t. That's the way they usually depict it. All right, and then we're going to use our basically our arc length notation here: dx dt plus dy dt squared over squared dt. So this is how we evaluate a function, the integral of a function over a particular curve. Instead of, incrementally in terms of x, we're doing increments in terms of that curve there. All right. All right. So let's just do a couple and see how we evaluate them. Okay, evaluate the line integral over c x y to the fourth ds, where c is the right half of x squared plus y squared equals 16. Okay, so step one is parameterizing C. All right, so here what we've got is a circle, the right half of a circle, and the way we parameterize a circle, if you recall, cosine squared plus sine squared equals 1 is the unit circle, right? Cosine squared t plus sine squared t. This one is radius 4. So in general, circle radius r can be parameterized with x equals r cosine t, y equals r sine t. Lots of different connections there, but so in this case we've got radius 4, and so our parameterization would be x equals, let's just do it right here, x equals 4 cosine t, y equals 4 sine t. Okay. Now, we just want the right half, though, and so t here would range from what to what? Negative pi over 2 to pi over 2 would be one way we could do that. So yeah, that would give us the right half. And notice with parameters, you do have kind of a direction there too. So we're defining this going counterclockwise. So, all right. Yeah, so negative pi over 2 to positive pi over 2 makes sense. Okay. Well, let's see what that means here to our line integral. So we'd go from a to b would be negative pi over 2 to positive pi over 2. All right, now x, well, we've got x is 4 cosine t. Y to the fourth would be 4 sine t to the fourth, okay. And then the square root of, we haven't done those yet. All right, so this is the square root of the dx dt squared, dy dt squared. So dx dt squared would be minus 4 sine t squared plus 4 cosine t. Yeah, so this is dx dt. I didn't write them down. And this is dy dt. It's also a part of this line integral. And then dt. All right, so that can get complicated there, of course, but in this case, it's not so much. Let's see, this would be negative pi over 2, pi over 2. Let's see, 4 to the 5th, is that 1,024? Yeah, because we got 4 and then 4 to the 4th, so I think that's 4 to the 5th, right? Cosine t sine to the 4th t is what we'd have on this side. Then the square root of, that would be 16 sine squared plus 16 cosine squared. Yeah. Yeah. Yeah, this, you're going to have square root of 16 times 1, so you're going to have another factor of 4, so we wind up with that. So yeah, this turns out to be really just a little simple u substitution, right, to evaluate that integral. You got sine to the 4th, so u equals sine. du would be cosine t dt, so we got it. So it'd be basically u to the 4th, so it's the integral from negative pi over 2, pi over 2, so it'd be u to the 4th, so it'd be well, 1024 times 4. What is that, 4,096? So we have 4,096 u to the 4th, so it'd be 1/5, u to the 5th, so it'd be 1/5, sine to the 5th, negative pi over 2, positive pi over 2. All right, so what do we got there? Sine pi over 2 is 1, so we got 1/5 minus negatives pi over 2 sine, it's negative 1, so we have negative 1 to the 5th, so that's negative. So it's is that 8192? It'll be 4,096 times 2/5, so yeah, that's 8192 over 5. That's what I get. Sound good?